Okay, 9.4, collisions in 2 dimensions. Well, we already know that for any collisions, momentum is saved, conserved. So no matter what, based on that, momentum in all directions X, Y, and Z is conserved. For any collision between 2 or more particles. Pretty standard. So what we're going to see today, we're going to see a billiard ball situation. We have a ball coming in, and this one a ball that's at rest. They're both going to hit and fly off in different directions. They're going to fly off at angles. So we need to treat that appropriately, the momentum in both X and Y plane directions. So it's very simple insofar, and I say that only in terms of what we've done before, in terms of vectors. We've treated everything in terms of X and Y. So it's the same thing going to happen for momentum X and Y. So the concept is easy, the same as we've seen thus far. So we're going to be treating collisions the same way. Collisions resulting in multiple directions in an XY plane. So just think pool table. You guys played pool before? Seen it being played? Collisions resulting in multiple directions in XY plane changes the conservation of momentum equation to account for the components. It could be X, Y, Z, W, whatever direction we're headed. So instead of having our typical M1 V1 initial, okay, we now separate them into components X and Y. Keep things simple. We can do Z when necessary. We will have, so we're saying the momentum of the initial momentum of the first ball in the X direction momentum of the second ball initially in the X direction equals their final components. And also in Y. So this is just the momentum in the X direction. So P sub X. And then P sub Y. And don't worry, we will do a clear practice problem over this. And of course, these x's and y's can become cosine theta, cosine phi, because in order to make the problem, I guess, more realistic, the angles are going to be different because most of the time your collisions are not going to go off at the same angle. So we have to generalize it. No, it should be sigma p's. There's no deltas here. We're not changing it. We're just saying that the momentum is the same on both sides. We're not taking a difference. Yeah, so no deltas. So this is our conservation of momentum in x and y directions. And now let's just run through the example that we have in our text. And we're going to do a example problem over this. The example problem is an allusion back to the problem that's going to be used as an example is an allusion back to the example problem in your textbook, which is example 9.8 on page 243, but we're going to do it hopefully simpler. Okay. At least with less nomenclature, symbology. Okay. Okay, so let's consider the collision of billiard balls. You know, when you play pool. So let's say the cue ball is coming in and it's going to hit an 8-ball. The 8 ball's at rest. And see what happens. So the cue ball is coming in, mass 1. Its velocity is, call it V1 initial x. It's traveling in the x direction. And then it glances, there's a glancing collision for M2, call M2 the 8-ball. And its velocity 0, he's at rest. After the collision takes place, the situation looks like this. So we have V1 final, so it goes off at an angle with the velocity. So we know a vector like velocity at an angle has 2 parts to it. It has V1 Fx, which we've detailed in the equation above. V1 Fx equals same thing as saying V1F cosine theta, where this is angle theta here. And then can just do this guy like that, I guess. I'll come back up top. So V2 and it said it goes off at 2 different angles, and this is angle phi to indicate that it's different than the angle above. So we have V2 to F sine theta. And then this guy up here is going to be likewise. V1Fy equals V1F sine theta. So we went from just a straight collision between the two balls, and now they're going off at different angles. They're going off at glancing angles. The angles are different. So in order to treat them equation form, this is like a free body diagram or just a diagram of the system, the picture of what's happening physically. Then we take the information there, put it into the equations, and let's get a picture of what's going on in equation form. Okay, so I just say all of the momentum in the x direction is going to be comprised of m1 v1 ix, the momentum of the first ball in the x direction, plus 0. The second ball has no momentum because he's initially at rest. Then they both fly off at different angles after the collision, and so then they'll have cosines of their momentum after, or we can just say m1 v1 fx m2 v2 fx, where v1 fx is v1 f cosine theta, v2 fx is v2 cosine phi. And then all the momentum in the y direction initially is 0. Obviously the second ball is at rest, he's not doing anything, but there's no momentum in the y direction for the incoming ball because he's going straight, he's going horizontal. So there's no momentum initially in the y direction there, but in the end, we have m1 v1 fy, m2 v2 fy, where this is cosine, or this is sine theta, and this is sine phi. Okay. Oh, but let me not be remiss on that. Let me see my signs here. Obviously, this is going downward, so this has got to be negative. So just the pure setup there, do we understand how that works? Do we see how that translates from the diagram to the equations? Straightforward. In the beginning, all the momentum is x, and the one ball, this guy's at rest. Then it's broken up into two parts. This is positive, this is positive. And in the end, this guy is going to be a positive here, v1f. This is v2f. This is going to be positive m1 v1 fy that we have here, positive, and this guy's going to be negative because it's going downward. And so that's just really, the setup that they gave you in the section 9.3, just going over that again. So rewriting that in terms of the angles, of course, some problems you'll be given the angle and you can just translate them over into the angles. So m1 ix plus 0, and this becomes slightly write this here. So obviously, if you had both of those angles, things would be easier. Life would be easier, but some problems you're not going to have those and have to do some crazy jumping around in order to get your solutions. So that's just the translation from V1fx, V1f cosine theta, V2fx, V2f cosine phi, and so on. In terms of the angles, breaking the components into their angles or in terms of their angles. And this one in the beginning is straight, so there's no cosine of anything. So let's do a sample problem that's similar to example 9.8. So I'll turn your attention to number 26 of your textbook. So yeah, collision two dimensions are number 26, page 262. So we have football season going on right now. Talk about football game. In an American football game, a 90-kilogram fullback running east with a speed of 5 meters per second is tackled by a 95-kilogram opponent, probably a linebacker, running north with a speed of 3 meters per second. Explain why the successful tackle constitutes a perfectly inelastic collision. Anybody? Who wants to tell me why that's a perfectly inelastic collision?
Is it because they cancel out?
I'm sorry?
Is it because like the energy on both sides would cancel out from them hitting?
Well, we can talk a little, we can say that in English. I'm just kidding. That when they hit together, they stick. Like when in a tackle, both of the guys are stuck together.
Yeah.
Because that, by definition of perfectly inelastic collision, we have two or more objects that hit and stick together. And that's what happens in a football tackle. Yeah. I don't have to get, too fancy. I mean, I know sometimes we have a tendency, and so do I, and all that stuff, but it's, yeah, straight up, it's the objects hit and stick together. By definition of perfectly inelastic collisions. But also to your point, though, the energies, well, they won't cancel out, but there's going to be some energy lost in that collision, right? So we know momentum is saved in any type of collision, perfectly inelastic, elastic, inelastic, which happens in reality. But the energy, some of the energy from the beginning gets lost in the collision itself at the end. And we've shown that a couple times. So let's put all the information here. Let's diagram it out, solve this guy out, and get the answer. Like part B, it says, calculate the velocity of the players immediately after the tackle. So we want to get that velocity of them hitting and sticking. So it's going to be a combination M1, M2, V final, right? And that's going to be a common velocity, obviously, for both. Then we can get fancy, go retroactive per the example 9.8 and get the angle of the collision. Not only are we getting the magnitude of the velocity and magnitude of the momentum, we can also get the direction, which is the angle of the collision. So, and then also in part C, we're going to get the mechanical energy that's lost, to your point, Emmanuel. Canceling out, there's some technically going to get canceled out or lost in the collision. So that's determine the mechanical energy that disappears, cancels, okay? as a result of the collision. Account for the missing energy. Okay. So what do we got here? Let me just do this by my picture I drew. All right. Okay, so here is the 90 kilogram guy. His velocity, say x, is going to be 5 meters per second. 12 miles an hour, something like that. And then, whoops, here is the linebacker. He's coming up. Boom. It's gonna tackle him. 95 kilograms. Anybody watch football out there? Football watchers? Now it is for sure. You know, all this corona. Yeah. Whatever, Nicole. No, I'm just kidding. Okay, so we have the final momentum there. Okay. So yeah, so after the collision, right. So we got that momentum going. And we have the momentum in the X direction and Y direction. Things are saved in all directions, right? So whatever this momentum is here is going to be the same in the X direction after, especially since it's all just made up in the, you know, by one player, and so, and conversely here. But we'll deal with that in the scope of the problem. Yeah, I made a writing things, thinking one thing and doing another. Yeah, you're right. V2YI. I don't like that. This thing gets stuck. All right, 1 second. And question. No, we don't assume 45 at all. You know, as a matter of fact, we can calculate exactly what it will be. So we're just doing it a little bit roguish. You know, we're not including the angle right now. Let's try to do it simple, get the components, and then we can get the angle. It may be 45, but who cares? You know, so let's just be bad boys and girls and not include the angle right now. Like I wrote before, so all the momentum in the X direction is going to be all the momentum, the X direction in the beginning is going to be equal to the momentum in the N in the X direction. So all of the initial momentum in X is going to be equal to the momentum in final in X. So M1 V1 XI plus 0. So I'm saying M1 is the running back. So all the momentum in the X direction is made up of, is held by the running back. And so the linebacker doesn't have any momentum in the X direction, just Y. And so these terms, or there's not going to be a Y term for the first guy. So they are going to hit and stick together, but that velocity is going to be in the X direction. I'm not looking at the hypotenuse yet because I'm just in X. The hypotenuse, of course, is a composition of both X and Y, Pythagorean. All the momentum in the Y direction for the first guy is 0. VFY. Okay. So far, so good. You guys get that? We're hitting and sticking along the hypotenuse, yes, but they have components of hitting and sticking along X and Y. Like the force equations, F, all the forces in the X direction, blah, 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 forces in the Y direction, blah, blah, blah. The projectile motion stuff. What are the equations for the X direction? It's just 1, and then there's 3 we can choose from in the Y direction. And, you know, then we can use Pythagorean to get the velocity along hypotenuse, or generally that's what we were getting, or whatever vector is along the hypotenuse. We can use the Pythagorean theorem. Okay, so let's go further. So the velocity along the hypotenuse, VF, is made up of VFX plus VFY. This is what is known as a linear combination, a technical fancy term in linear algebra, that meaning that this is a combination, a linear combination of these two terms that make up this term VF. And so this right here is the vector representation. And so, of course, when we look at it in equation form, we're looking at the magnitudes in those directions. So this is the straight vectorial linear combination of VF. It consists, or it's a sum of everything in X and Y. So that being said, we can find the magnitude of this, VFX squared, VFY squared, by using Pythagorean. So let's solve for VFX, solve for VFY, plug it into the Pythagorean. We have our final answer, VF, and then we can get our angle and we can get our kinetic energy, all that. I encourage you to look at that proton-proton collision example. Very nice. That's what, you know, you're solving problems like that, and you know, you're really building some muscle, physics muscle. Which I know all of you, you're getting it, getting there now. Okay. So I'm going to take the first look at the PX equation and solve for VFX. And this was going to be, right? So I'm solving for VFX, so just divide both sides by M1 plus M2. And then mass 1 is 90 kilograms and 5 meters per second over 90 plus 95, which is 185. Then do likewise the same with VFY. Let's see, ones and twos on the ones and twos. All right, so this is going to be 95. And that's it in Pythagorean, that guy. That's going to be 2.43 meters per second along the X direction. That they're moving along that, that's their component. VFY is going to be 1.54 meters per second. You know, when I evaluate that. Then get to VF is the Pythagorean of both, 2.43 squared. That'll be 2.876 meters per second, approximately 2.88 meters per second along the hypotenuse. Questions? Oh yeah, yeah. Tell me when to stop. Oh, you want the equations? Okay. Yeah, I mean, hopefully it's not that bad. Hopefully, break everything up X and Y, just until or not. Maybe right now you can just see the whole picture. Like, okay, I don't have to do all that. You know, I can see where it's going. That's great. But in the beginning, if not, break everything into X and Y's as needed. We're trying to get the VFX, VFYs to get the VF, and good. Okay. Okay. So now it's a sense question. We got the magnitude. Now let's get the direction. So that's easy, right? We can get the components of the velocities and do this guy. I mean, it would be 45 if these are proportional to 3, 4, 5 triangle, but I don't think it is. But VFY, VFX, okay, and then theta. Okay. So VFY was 1.54. And this is 2.43. So go ahead and solve that, but you know, I'll come back. So I just wanted to make a note to make sure that you don't think that this was an arbitrary right triangle. Well, this guy's going east and north, so when you add them geometrically, you know, tip to tail, this is going to be at an angle direction like this. And so our angle there, 5.4. Okay, 0.633. 32.3 degrees is the angle of impact. That's the direction. So even if you did, which would be, you know, you could cut out this last step, but this is not bad. I mean, you've seen this before. You could, instead of saying your V1 FXs and stuff, you could just put the angles in there. Like this will be VFY2 sine theta and VF1 cosine theta. And then you're going to get a tangent expression and all that stuff. But I like this way. You may like the other way. Questions on that? Little bit.